So in today's lesson, I want to continue our conversation around stock solutions. And at the tail end of yesterday's lesson, we looked at what a stock solution is. And essentially, what a stock solution is a super concentrated solution that we take little bitty bits of and we use that and dilute it in order to make solutions of varied concentrations. So yesterday I brought out my big jug of conc HCl, my stock solution of HCl, which happens to have a molarity of 12 moles per liter. You'll remember it's kind of syrupy, fairly viscous. So what I would do is I would use my graduated pipette and I would pipette the required amount of my stock solution, and then using a really precise instrument like a volumetric flask, I would go ahead and make my dilute solution, right, by adding water up to the little glass mark on my volumetric flask. Now, one thing we didn't talk about yesterday is how to go about making an acid. So chemists will say add the acid to the water, not the water to the acid. So just think about that alphabetically, right? So I'm going to add acid to water, A and W. And not the other way around. And the reason for that is that if I were to just add acid in the bottom of this volumetric flask and without diluting it and then add water afterwards, I would get these nasty vapors popping up, and it can be quite nasty. So the solution to that is to just add a tiny little bit of water in the bottom first half of this volumetric flask, right? And then add my acid next, and then fill to the line. So that just prevents some injuries related to mixing acids. You can also get lots of heat released and so on and so forth. So that's a safe way that you want to make a standard solution. Incidentally, while I was perusing the internet for nice pictures of volumetric flasks, I happened to come across this picture, and what this is it's an exhibit, a Harry Potter exhibit somewhere, I don't know where it was, but where there was actually a volumetric flask. If you look really carefully, here's a volumetric flask. And I was kind of a little bit ticked off because, no real chemist would ever use a volumetric flask in this fashion. So a little bit disappointed by the people who organized this Harry Potter exhibit. Doesn't look very authentic. Anyways, moving on. Okay, so one idea that I want to make clear to you is that, when a solution is diluted, the number of moles will remain the same, but the volume of the solution will change, right? So let me explain what I mean by that. So let's say I have a solution where I have, let's say, 3 particles in it. I'm going to call those particles just particle A, just randomly, right? So here I go, sort of like an A, I guess. And so I have those 3 particles in a certain volume of solution, right? So let's just say that my solution is about yay high, right? And so let's say then my next step number 2, is that I'm going to add some water in there so that my new volume of solution is greater than what it was before. But the reality is that because I haven't added any more particles of A to that solution, that I still only have the same number of moles of particles, really, but just in a greater volume of solution, right? So that's what happens with dilution, and that's a really key point, is that I'm not increasing the number of moles of particle A, I'm just increasing the volume of solvent and total solution that those particles are in. And so I could also talk about evaporation in sort of the same context, where I could say, well, let's say I evaporated some water, right? By evaporating water, I'm still going to have the same number of moles of my solute, right? So I'd still have, in this case, 3 particles of A, same number of moles, just in a lower volume of solution. So by evaporating off my solvent, that reduces the total solution volume, and thereby increases the concentration. So I want to share with you a formula that is commonly used in order to perform dilution calculations. There are mechanisms by which you can just sort of look at the units and have an understanding of the chemistry to solve problems involving dilution. But I think the formula may be useful to some of you, and so I think we're gonna give that a roll in terms of solving these problems together. So let's just make sense of what this formula means. C1V1 equals C2V2. So you may have already guessed what the C stands for and what the V stands for, but what about this 1 and this 2? So C1 in the context of this formula represents the initial or the first concentration. So initial concentration. So that can mean your stock solution that you're starting with, or it can just be some random solution that you have at the beginning that you want to alter in some sort of way by adding or removing some of your solvent. So most of you have probably guessed that V represents volume in this case. So, and you're right, but what do I mean with V1? Well, if C1 means my initial concentration, my starting concentration, then V1 represents the volume of that initial solution that I need with the given concentration indicated. So as you would expect, my C2 represents the final or the second or the desired concentration. Okay, so I'm going to call that the second or the final concentration. And usually that's the one you're looking for. So, lastly, let's just finish this off. It should make sense to you that V2 represents the volume required or needed given the final concentration, right? So that's my final volume. So the volume that's associated with the solution with the concentration that you're looking to get, right? So this is my final volume. Just a note about units here. So you'll notice that concentration and concentration are on the, those are on opposite sides of the equation here. That means that, as long as the units for C1 and C2 are the same, then they will cancel accordingly. So that's kind of handy. So in other words, if my first concentration is in moles per liter, then that means that I'm solving for a concentration that will be also in moles per liter. If I had concentration in percent, then my C2 would also be in percents, and so on and so forth, right? So in terms of volume, the nice thing about this too is that as long as I have the same units substituted for V1 and V2, then there's no need to convert because those units will cancel if a concentration is what I'm looking for. Again, I'll just explain all of this as we go through a couple of sample questions with you. Another point that I wanted to mention is just the notation involved in concentrations of solutions. So the word concentration will often be, instead of writing it out, what you'll do is you'll symbolize it by writing square brackets around the particular substance. So for instance, let's say I wanted to find out the concentration of hydrogen ions, then I wouldn't write concentration of H+. I would symbolize that using these squared brackets. And when I write it like that, that really just means that I'm looking for the concentration of H+. All right, so let's take a look at our first problem here. So the question says, how would you make 350 milliliters of a 0.20 mole per liter solution of sulfuric acid from an 18 mole per liter stock solution? So let's start with our handy dandy dilution formula. And we know that means we need to somehow extract all but one of these variables. So let's start to break down what's going on in the problem itself and try to make sense of it. So it says, how would you make? So in other words, this is, this 350 mils right here, this is the volume of of the solution that I want to make. So right there off the bat, I have my V2. That's what I want to make. So it's my final volume. So I'm going to just write that down. So V2 is equal to 350 milliliters. And I'm just going to apologize right off the bat. I'm sitting at home here doing this without my smartboard, so I'm doing the best that I can with this little writer program that comes with Screencast-O-Matic, but it's doing its job, so it's working out. So there I go. So I know that 350 milliliters is the final volume of solution that I want to end up with. All right, so moving on. I also know that the concentration of the solution that I want to make, will have a concentration of 0.20 moles per liter. So I'm going to write that down. What does that represent? That is my final concentration, so that's my C2. This is kind of brutal. Anyway, moving on. So 0.20 moles per liter. All right, what else do I have? It looks like I have an 18 moles per liter stock solution. So that's my C1. So I'm going to write that out as one of my givens. So C1. And that's my 18 molar solution. All right, so it seems as though the only thing I don't know is my V1 in this situation. And so let's analyze why it makes sense that V1 would be what I need to figure out here. So it says, how would you make 350 milliliters of a 0.2 mole per liter solution of sulfuric acid from an 18 mole per liter stock solution? So they're really asking me how much of this concentrated solution am I going to need to draw out with my pipette? So it's going to be a small amount. And then dilute to a volume of 350 milliliters with distilled water, right? So I'm going to expect that my volume of my 18 mole per liter solution is going to be a whole lot less than 350 milliliters. And if it's not, then I've made a mistake somewhere along the lines here. All right, so let's sub in what we know. So I know that C1 is that 18 mole per liter. And my V1 is what I don't know. My C2 was that 0.20 moles per liter. And my volume is 350 milliliters. And I'm fine to use that 350 milliliters because as long as I remember that whatever volume I find for V1 is going to have units of milliliters, then I'm good to go. All right, so isolating, hopefully you're all fairly comfortable with it. To isolate V1 in this case, I'm going to divide by 18 to get rid of the 18. Divide that out. Whatever I do to one side of my formula, I'm going to do to the other. And so when I isolate V1, whoa, that's really big V. I get, rounded to 2 sig figs, 3.9 milliliters. So, I'm not going to write this out here, but let's just have a conversation about how I would finish off this question. Remember, the question's not asking me for the volume of my stock solution required. It's asking me how to make this solution. So I would not need to add details about how I would take my volumetric flask, add a small volume of water to the volumetric flask, pipette 3.7 milliliters of my stock solution into the volumetric flask, and then dilute to a volume of 350 milliliters with distilled water. So there I have it, done. All right, so here's our next problem. I've called it problem number 3 by accident. It's really just problem number 2. So let's read it out loud. So I have 25 milliliters of a 6 mole per liter solution of nitric acid. And then, I take that and I dilute it by adding 125 milliliters of water. And I want to know what the new concentration of the acid will be. So before we start, we should look at what a reasonable answer would be in this case, right? So I'm taking a small amount of a concentrated solution and I'm adding water to it. And so I would expect that proportionally speaking, my concentration should go down by quite a bit. And so if I get a value that's higher than 6 moles per liter, then I've screwed up somewhere and I need to analyze what I've labeled as for each of my variables. So let's start with our dilution formula. Now I think it's a good idea to write out our givens. Now you may not feel the need to do that necessarily, but I think it's good practice. So let's just to make sense of what components of this problem are going to be on each side of the equation. So I'm starting with 25 milliliters. So because that's my starting volume, I'm going to call that V1. And the concentration that matches the 25 milliliters, in other words, I have 25 milliliters of which concentration? I have that of the 6 mole per liter solution. So I'm going to write that out. I'm going to use the capital M here just to save us the time. And then I'm going to add 125 milliliters of water. So some of you are probably thinking that V2 is 125. And you'd be wrong, because if we conceptualize this problem, just imagine, right? So I have a container, presumably, that at the moment has only 25 milliliters of solution in it, right? But then I'm going to fill to a volume of 125. No, I'm not. I'm not filling to a volume of 125. I'm filling by adding 125 more. So I have my 25 down here, and then I'm adding 125 more. So what is V2? V2 is 125 plus 25, right? Because I'm adding that 125 milliliters to a previous volume. And so I want to know, well, when I add that volume of water to the mixture, what can I expect the concentration to be? All right, let's plug some values in here. So I have 25 times 6.0. And that's equal to C2, which is my unknown, times V2, which I actually do know. We just talked about that. It's 150 milliliters. So I'm going to solve by isolating C2 again by dividing out its coefficient. Divide by 150. That will cancel out those. They get divided out. Whatever I do to one side of my equation, I'm going to do to the other. And so either using my calculator or using mental math, 25 times 6 gives me 150. Divided by itself gives me 1. I'm going to look at sig figs. I know I need 2 significant digits here. And so that tells me that the resulting concentration after dilution is not just 1 mole per liter, but 1.0 moles per liter. So notice in this question, it doesn't tell me how to make it because they already tell me what I'm doing. I just needed to find the resulting concentration. So therefore, since C2 is 1.0 moles per liter, I can therefore say that the concentration of nitric acid, HNO3, is 1.0 moles per liter. And that is a value that makes sense in the context of this question. So that's all I got, folks. I think you'll manage these questions quite well. You'll notice on Google Classroom that I've attached a PDF of a worksheet that I'd like you to work through with the answers as well. And so if you struggle with any of this, make sure that you come and see me early on Friday morning. Remember that we have a quiz on on Friday at the beginning of class on everything we've learned in this unit so far. Talk to you soon.